All right. Hello, everyone. Welcome to today's special meeting. Today, we are in the second week of October, and this means we are right in the middle of the Cloud Native Sustainability Week, the CNCF Cloud Native Sustainability Week. We already had lots of meetups, in-person meetups, and this meeting is a virtual one just to complement all these in-person meetups, just to give like a platform that everybody can join also like one of the events, because we don't have the option to organize an event in every single city, of course. But I think so far all these events are going very great. All the comments, all the posts are very exciting. So thanks everybody for joining. We have quite a few talks for today. I'm very excited. It's looking to be very, very interesting. Before we get started, my name is Leo. I will be the host for today's meeting. And with me is also Nancy. She will co-host. So if you have like any questions, logistic questions, something like this, you can drop us a message. Please be aware that we have like quite a few folks in this meeting. So if you have like any questions, you can drop those in chat, and also unmute yourself if you like to, but just be aware of that. And yes, as I also mentioned before we start the recording, we initially planned to host this on Bevy, which is a platform used by the CNCF community to host virtual events. But we had a couple of technical questions or problems, I would say. So we are jumping now over to Zoom, which we all are familiar with. So maybe a few folks will trickle in over time, but this should be fine. All right, let's get started. So for today, we have 3 talks and a couple of project updates, also a small introduction. We have also a schedule, which is published on the community page. You probably already saw that. But probably we will deviate a little bit, like a couple of minutes from that schedule. We already did by postponing this kickoff like by 5 minutes. So if you are interested in one particular talk, maybe join like a little bit earlier or a little bit later, depending on that. But as I said, this will also be recorded. We will do our best to stick to those times, but I don't expect that this meeting will go much longer than we initially planned. Yes. Before we start with the first talk, a quick introduction to the Cloud Native Sustainability Week. I already see a couple of local meetup organizers and in general, like people who helped with the overall organization. So I guess most of you are already like familiar with what we are doing this week. So the CNCF Technical Advisory Group, one of the major things we are working on is outreach and advocacy in the community. And the Cloud Native Sustainability Week is one of the projects we were excited about and scheduled around outreach and getting people just aware of what is Cloud Native Sustainability. So in this event, which we planned half a year ago, or we initially planned, or like the conception was like half a year ago. The idea was that we have like a global problem. Sustainability is very much like a global issue, and we would like to tackle this also globally. And with the CNCF, we have a global community, so we want to kind of engage the best we can this global community in this efforts. So we have a bunch of local meetups. 20, 21, 23, it's like a changing number. Organizing meetups is more challenging sometimes than you expect. So there are a couple of meetups joining and getting postponed, but we are around this number, around 16 different countries. We have local meetups this week. So that's, I think, a very exciting and high number. A lot of blog posts, 6 blog posts this week around Cloud Native Sustainability. this virtual event, which we are joining in right now, and also a daily live stream on YouTube all around this topic. So our hope is that with all these different initiatives, written information, like live information, in-person information, all these discussions, hopefully we can drive a lot of energy in these topics and learn from that. And also the CNCF TAG Environment Sustainability projects, which we have short introductions later. Hopefully we can funnel some of this information into those groups and learn from that. And all this information is obviously at the website. So if you're interested in any of the meetups or the live stream, for example, you can check out the website. There is at the top like a header, Cloud Native Sustainability Week, with all the information. Yes, and then just one note before we start with the talks about the CNCF Technical Advisory Group. Most of you are probably already familiar with that, but if not, the CNCF is a open source foundation, obviously, and with that, there are a lot of contributors and people who are putting in their free time to work on open source software. And over time, with the growing community, there are certain themes are building up. So we have a technical advisory board or a technical oversight committee. And with that, also for certain domains, technical advisory groups. So there's, for example, a TAG storage, a TAG security, and for all like major domains. And last year, exactly, I think in October last year, we started the technical advisory group for environment sustainability, just to complement that, because we observed over the last years, this is like a emerging topic, and it would be great to just to have a community group to build more knowledge in the community around these topics and to drive and mature this field in the CNCF community. So if you're interested in joining, again, you can check out the website. We have every 2 weeks the official meeting, but over time we started like sub-projects and working groups, and they meet at also regularly every week, every 2 weeks or so. So if you're interested in any of these topics, which we will also present later, these are all public and open. So you're happy to join in. This is one of the goals, to find also some people actually to contribute to those projects. That would be great. Yes, and because we are already on the subject of TAG projects, so you can see like a couple of projects which we are currently working on, and we are also presenting today after the talks. Are, for example, the landscape document, which Malo will show a little bit later, the CNCF Green Reviews project, which we started in August this year, about just measuring the sustainability footprint of CNCF projects. And the goal is to, over time, just improve, first of all, the observability of the footprint, but also to decrease the project, and that end users are kind of familiar actually with the footprint, and that they can make like an informed decision in a way about that. And then the working group for communication, where this project kind of falls under. This is also one big part. And a couple of projects, these are just two which we are planning or looking into, for example, maturity model, and also a Kubernetes sustainability deep dive, which is obviously, because we're in the CNCF, I think a natural fit. So there's a lot of projects which we are looking into, but this depends a little bit, or very much also on the contributor base. So where are people interested in? But we have a lot of projects planned. You will hear more about the 3 ones which are like darker highlighted later today. And the last slide is how to get started or how to engage with the tag, which is one of the most frequent questions I usually get. And I think it makes a lot of sense. So in the CNCF, everything what we do is public in a way that we have a public repository, and all the artifacts which we work on and publish are pushed through this repository. For example, if there's like one project, for example, the Cloud Native Sustainability Week, you will find a bunch of issues where we communicate about that. So if you're interested in any of that, you can just jump on those issues and comment that you're interested. And next to these issues, we have meetings to complement that and to discuss this. So usually this is like a very straightforward approach how to get started with open source in a way. So if you're interested also maybe not in the tag environment sustainability, but maybe more in tag security, this can also be like a good reference for you for these groups. Right. And not the last slide. This is actually the last slide about the attendee survey. So we shared at the local meetups a survey about just to reflect on the event, but also to share their thoughts. Because as I said in the beginning, in the introduction, one of the main ideas to organize this event was to have a diverse field of just like what people are thinking about the space, where it's going, what are they are working on, and so on. And it's we want to expand the survey also to the virtual realm, so to say. So we have this attendee survey also for everybody who is attending right now, but also we post this later on social media platforms just to get more information, a better overview about the landscape. So if you have like 2 minutes, I think just 7 questions or so, it would be great if you could share your thoughts. And with that, I will transition over to the first talk. So I will stop sharing my screen and you can directly take it over.
All right. Thank you very much. My name is Asser Tantawi. Let me share my screen here. And I'm with IBM Research, stationed in New York, Yorktown Heights. That's in the state of New York. What I would like to share with you today is a project that we're working on. I'm jointly working with Tayeba, who will show you a demonstration later on a project that we call Caspian. It's centered around Kubernetes, and it's built on top of Kubernetes using open source assets. And the project is called Caspian, standing for Carbon Aware Scheduling and Placement of what the workload that we're considering is mainly AI, ML jobs. And we're looking at a multi-cluster environment. Let me do this in this mode. Maybe that's better. All right, so let's jump in. The agenda is I'll give you a little bit of a background and motivation for why we're working on this. What is the problem that we're tackling? Some prior and ongoing work along those lines. I'll give you an overview of what Caspian is, touch upon the optimization problem that we're dealing with, and if we have some time, we'll get into architecture and design. And we'll share a quick demo of the functionality and capability of this project. So I don't have to tell you this, but we're all aware that these AI models, especially the newer ones like GPT and so on and so forth, they consume a lot of energy, and because of that, they produce a lot of carbon emission out of those. And these are just a few samples that I picked from here and there. There's a lot more. Trying to assess, put a number on, how much carbon really are consumed by these kinds of applications. And we're talking like, they specify that in in pounds or tons or whatever, but more interesting is the equivalent of that carbon emission to how many round trips or how many trips you make in your lifetime in a car or household, or even I read recently something about AI. If we don't do anything about it by 2027, just running an AI training is like equivalent to whatever the power that is consumed by the entire country of the Netherlands. In any case, so we know that these jobs take a long time. They use GPUs and what have you. These are power-hungry devices, and they produce a lot of carbon. And this is not a point in time. It's getting worse, as a matter of fact. As shown here in some of the diagrams, the slope has, in the last 10 years or so, increased quite tremendously. And what you see here on the y-axis is power in terms of computation, like petaflops, and it's increasing. And the equivalent, as I said, like, it's like 5 times the amount of energy, the carbon that you produce when you're driving a car, and so on and so forth. So given all this, what can we do about it? So here is looking at the way the generation of electricity. So I'm running these jobs in some data center, and that data centers gets power, electricity from the grid. What goes into the grid is the production of that electric power that comes from various sources, of course, solar, gas, wind, nuclear, and so on and so forth. And that mix varies from place to place, as shown here as examples. But more importantly, I mean, that is important, but also it changes over time because it's night, day, and so on and so forth. And not only that, the grid itself is buying energy from these sources, and they are solving their own optimization problem to figure out what source should they get energy from at what time. So that mix changes over time, and the mix varies by location. What matters is something that is known as the carbon intensity. And the carbon intensity is a function of the mix, and it changes over time. And the way the carbon intensity is computed is you take the source of that energy. Each source has a certain multiplier, if you will, which is how much carbon is in it, right? Coal is high, nuclear is much less, and so on. And so you multiply those by, at any point in time, by the ratios of these sources, and you get eventually a carbon intensity that changes over time at that location. And there are services that provide those numbers. They typically change every 15 minutes, maybe half hour, something like that. So they don't change that frequently. Right? You could predict what's going to happen in the future based on the past. There is some repetitiveness, kind of. Though there are factors such as we don't know what the weather is going to be like, the wind condition, and the sun, and so on and so forth. And also, as I said, there is an optimization problem that the grid provider is solving. So it's hard to predict, but people have worked on prediction as well of that. So let's get into the main, at a very high level here. I'm looking at a job, one of those AI, let's say, training job, takes a long time. What is the carbon emission of that job? Well, you have 3 quantities that are multiplied by each other. You have this carbon intensity that we talked about. You have the power consumption, and you have the job duration. So carbon duration is in time, let's say in hours. Power consumption is in power, as in watts. So you multiply these 2, you get power hour or kilowatt hour or something like that. And carbon intensity is carbon per kilowatt hour in grams or tons or whatever. So if I want eventually to minimize my carbon emission for that job, I'm going to have to minimize one or more of these quantities. Lowering and it's a product, so lowering carbon intensity involves the smart selection of time and place, as I showed you in the previous chart. Lowering that quantity power consumption would involve selecting maybe more efficient hardware, have a better, smarter way of scheduling jobs on hardware. Minimizing job duration has to do with maybe shorten the time by using more efficient algorithms, by adjusting hyperparameters, and so on and so forth. The focus of this talk is on the first one, is on how you select time and place to run the job. Okay, so I'm here stating the obvious, which is if you want to minimize the carbon footprint of these jobs, right? So schedule the jobs wherever and whenever renewable energy is high. That's when you're going to get your carbon intensity to be low. There have been some talk about that for a while. I mean, Google talked about that a couple of years ago, I believe. At a very high level, what you see in this diagram as time is x-axis, and this grayish thing is the carbon intensity. So let's assume it increases during the day and it comes down. And you have some kind of a load. These are the jobs that you have to run in that location, right? So in yellow is the base load. Suppose it varies over time like that. If you're able to somehow change that and make it, if it's flexible, right? And you get the green one, so you're pushing some load further down at this area or that area where the carbon intensity is low, and you're pushing down when the carbon intensity is high, meaning you perform less work, then that's ideal. How do you do it? First of all, is it doable at all? Maybe you can postpone things, but how do you move them further up? If they are scheduled jobs ahead of time, maybe you could do that. And if you're going to postpone things so that you can take advantage of time where the carbon intensity is low, well, there is a disadvantage there that you're delaying jobs, and there might be some tolerance to how much delay a user is willing to accept. So one has to set up this in a clever way. Right. So I mean, we talked about open source and stuff. And here what I'm showing is where I'm really concentrating, which is in that area. This is a hierarchy of what you can do in a data center, starting from the lower power sources and how do you make the facility more efficient, how do you use better resources, and so on and so forth. But this talk or this project, Casbin, is focused on a multi-cluster thing, that you have multiple clusters, different geographical locations potentially, and you have these long-running jobs that you want to schedule. So that's the picture of what the problem is at a very high level, that you have jobs coming in, they queue, they have a target deadline that you have to finish by. That deadline could be hard or soft. You have different locations, and because they are geographically potentially all over the place, then the carbon intensity may vary, and it varies over time. So how do you schedule jobs to locations at different times while minimizing the impact on the deadline? There has been a lot of work going on. There is this particular piece of work, I don't know how to get rid of this thing, that has to do with how do you predict these carbon intensities that I talked about. Here's another piece of work that talks about a very similar thing, which is if you can move your scheduled workload back and forth in time, you take advantage of low carbon intensity durations, or if you are able to take that workload, that job, And if you're able to break it into pieces, right, so you preempt it and you schedule the pieces at those locations, at those time windows where the carbon intensity is low. So if you're able to move the job either back and forth, or if you or you break it into pieces, you get advantage. And this piece of work here tries to assess how much advantage you get in terms of reducing carbon by doing one and the other. You look at various parameters, depends on how long the job is. For example, here, depending on the length of the job. Obviously, if the job length is very long, spans weeks, then you're not taking advantage of the time when the carbon intensity is low. So you get more advantage if the job is small. Uh, that's what this study is showing. So let me jump into what we're trying to do here. So our approach is we formulate a global optimization problem. We have these bunch of jobs that we need to schedule at those locations at different times. And our aim is to minimize the total carbon footprint for all the jobs, not specific jobs, as the sum of all, by placing those jobs and making sure that the resource constraints are satisfied. Jobs have resource requirements and we have to satisfy that. Job have latency requirements and we have to satisfy that as well. It's a time slotted system, so we solve this up because it's costly to solve an optimization problem. So we try to do it every like half hour or something like that, given that these jobs are long running. So it's batch scheduling in that sense. We make some assumptions that the power profiles of let's say CPU is linear, and that's an acceptable kind of assumption. It simplifies the optimization problem a bit. Since we don't know what the actual usage of a job is before it starts, so we assume that whatever it's asking for is proportional to whatever it's going to be using. Most likely, if we're looking at GPUs, for example, that's what typically happens. You ask for four and you use all of them. So in this project, we're not concerned about placement within a center, like on which uh, node or on which physical server you're going to place things, and also the scheduling within that time slot of half an hour, let's say. So this is the big picture. As I showed before, we have a queue. We have jobs that are not running yet. We have multiple data centers. They have different capacities of resources. They have different characteristics of carbon intensities. How do we do the scheduling and dispatching? Okay. Obviously, I'm not going to go through this particular formulation of the problem, but it's an optimization problem at the end of the day. In this case, it's an integer one. Where the variables are for each job, where do you run it, and in which time, at which time location. Satisfying some constraints shown here in color. So obviously you want to make sure that the resources are satisfied. You want to make sure that that jobs are executed. Yeah, there may be some restrictions, like even if you break it into pieces, you don't want to send pieces to different locations if that's the case, um, and so on and so forth. So in our uh, path to solving this problem, we actually started with, so it's all on Kubernetes, and what we started with, because we're dealing with multiple clusters, with this project that's called KCP, stands for Kubernetes Control Plane. I'll show a picture of that. And then we moved on to just bare Caspian on multiple clusters. And then currently we're working on Caspian on kubesteller. That's another open source. You can go to kubesteller.io, and it's really based on KCP. We do have a couple of publications that get into the details of optimization if you're interested, and they are shown down here. So let me talk a bit about, I don't know how much time we have, but I'm assuming another 10 minutes. So let me spend 5 minutes on describing a little bit of architecture, and maybe I'll give the floor to Taibat for 5 minutes to show a demo. Okay, so what you're looking at here is we have a multiple physical clusters. These would represent the various locations. These are Kubernetes clusters. And we have the control plane, which is, in this case, is using KCP Kubernetes control plane. And that's the control plane of Kubernetes without any nodes. So nothing that runs in here. These are all, they're called workspaces. You could have the Kubernetes objects. And then we have our controllers running here in its own cluster and in some control cluster. Okay. So we needed to add a couple of custom resources, if you're familiar with that terminology for Kubernetes. A custom resource that we call a green cluster, and that's an object that lives in the individual physical clusters that captures how much resources are available on that cluster, CPU, memory, GPU, and what have you, as well as carbon data. So that would be like a time series of carbon intensities at that location, as well as predictions in the future. And there is a controller cluster monitor that keeps updating those green cluster objects on the physical cluster. Sorry. As far as user is concerned, submits a job. A job could be, in Kubernetes terms, could be a job. It could be an array cluster, PyTorch, or something like that. Okay, so the second custom resource that we added is something that we call the green job. And that's like a manifest of the job. So it has the specs of the job, resource needs, deadline, so on and so forth. And what our controllers in Casbin will do is select or set a target field in here in the spec, which is the target cluster, right? And it will also set the time. When should this job start? And that's set by the scheduler. And the scheduler uses an optimizer, which solves the optimization problem that I showed you before. Well, how do you solve that? You can rely on a solver that solves a mixed integer linear programming problem, but because of just the size of this problem, you cannot just simply use an off-the-shelf solver. So we needed to provide some approximate methods to do that efficiently. And that's what's shown in these couple of papers that we have. In any case, we have an optimizer that's called by the scheduler periodically, as I said, maybe every half hour or something like that, looks at all the jobs that don't have a target set or a scheduled time set, picks them up and figures out what's the best target and scheduled time. For the jobs that are already running, we might also have to alter that by preempting them because there is another job that is a higher priority or its deadline is coming soon that that we need to preempt a particular job to dispatch this other higher priority job. How do we do the wiring? For once that is set, we have another controller here that looks at whenever a green job has a target set, then it does the wiring. The wiring means that all objects in a particular namespace that is assigned to the user is going to be mapped to a particular physical cluster. Mapped meaning what KCP will do is all objects that live in this namespace will be transparently, the user will not even be aware of where the job is running, will be transparently synced down in this namespace down here in that particular target physical cluster. And the job status will be also upsynced to so that the user would know what the status of the job is. So we moved away from KCP and we tried similar kind of thing or the same functionality without that by having a master kind of controller cluster or a hub cluster, if you will, and the same bunch of physical clusters. And in that environment, we provide to the user, instead of running up here in the master cluster, will give the user a namespace and a controlled namespace, and will give the user a context that he or she would run whatever resources needed for that job in this controlled namespace. Again, using the same optimizer, the same scheduler. And finally, and that's what we're currently working on, is use kubectl, which is another mechanism to provide this transparency. It's a bit more involved, and I'm not going to get into details of that, but using the same kind of things, these green cluster objects and green job objects to again solve an optimization problem, set the variables, and let kubectl do the rest. And I'll stop here and pass the baton to Taiba, if you could just show a demo.
Thank you, Asser. So let me share my screen. Okay, so I think we have 4 minutes, so I will go very fast over the demo. So here you can see multiple windows, so I'm going to explain them one by one. But so here we did like 2 sets of experiments. The first experiment is with Caspian, in which we have an optimizer with the concern of carbon footprint. The second concern, the second objective here is like the tardiness of workloads, the minimizing the completion time of the workloads. So another schedule that we use here to just compare how Caspian how is the performance of Caspian is QoS space scheduler. So in which the scheduler schedules the jobs to minimize the completion time of workloads. Okay, so on the top of this demo, you can see the output of the system when we use QoS scheduler, and on the bottom, you can see the output when we use Caspian. Okay, so, and then in the left, the most left-hand side, you can see a figure that shows the carbon intensity of clusters. So for this demo, we have 3 clusters, one in UK, one in Ontario, Canada, and the other one is in New York. And the carbon, you can see the next, like the carbon intensity, predicted value of carbon intensity in the next 24 hours. And so obviously the one that is in UK has the lowest carbon, the second one, and then the third one has the highest carbon intensity. So then let's see. So then after that, you see 2 terminals that shows the status of jobs. So then in the middle, you see the CPU utilization of these 3 clusters. And then at the end, you can see the carbon measure. So carbon measure, so let me play this demo, I'll explain it later. So first of all, so you see the jobs, so we use the same simulations, environment, the same arrival rate of jobs and the same clusters. So now here you can see the jobs are submitted to the system. And then, but if you look at the state of jobs by QoS, you see these jobs are scheduled earlier compared to the one to the Caspian, because in the first one, just schedule them as soon as possible, while in the second one, we postpone them to schedule them in low in time slots where carbon is low. So you can see that how different they are in the time that they are started and they are running. And so we see kind of like balanced resource utilization for QoS-based scheduler, while with Caspian, we see the higher load is assigned to the green cluster. So, and you can see at the right-hand side, you can see the carbon measure of each approach. So the one that is on top, with QoS, you see the carbon measure. Carbon measure is like a metric that shows the total carbon per hour, and that's the one that on top, and then carbon measure shows like the accumulative carbon till this hour. So you see how different is the output of these two approach. So with Caspian, for example, the total carbon for this experiment is like 10,000 units, while with Caspian, it's like 15,000 units. So, yep, that's it. Let me stop sharing. Here and
Just a correction. That I'm sorry, Taiba, you said 10,000 for 15, 10,000 for Caspian, and the other one was 15,000. Is that correct?
oh yeah, maybe I
Maybe
mean,
it was the other way around, or maybe I heard it.
yeah, I mean, the lower value was for Caspian.
Caspian did better. That's at the end of the day, Caspian has to do better.
Yeah.
All right.
For that.
Thank you. Any questions? All right. Thank you all.
All right. Thank you very much. This was very interesting. So could you perhaps also share afterwards because this is one of the questions, the slides. I can also upload it to one of our community drives. I see a couple of folks were very keen to dig into the slides again.
Sure.
Awesome. That's great. And there were also a couple of comments by Adrian. Not sure if you would like to talk about that, but if not, we can also move to the next presentation. And after the next one, so this one will be like a lightning talk, a little bit shorter. And after the next one, after this one, which is coming up, we will have a short break, 5 minutes, 10 minutes, 10 minutes maybe break before we head on the rest of the event. Eduardo.
Hey, hello everyone. How are you? So let me share. Can you hear me? Well,
Yep.
Yes.
thank you. So let me. Well, let's do it. Hello everyone. Welcome to our session today, where we talk about container sustainability with different approach to make it possible. I have a thought about different way to sell my talk, my lightning talk. Maybe saying the magic word generative AI sustainability or other, but today it's something that really needs to be done. So who I am, I'm Eduardo Spotti. I'm currently a solutions architect at Amazon Web Services and founder of Crubit, an innovation consultancy agnostic to commercial or cloud providers, and mainly focus in adoption of open source practices and tools, mainly in DevOps, cyber reliability engineer, and cybersecurity contexts. I worked in other roles in big tech companies in Latin America, such as some of those seen in the presentation. If you didn't notice, I'm from Argentina, so it's very important for me to be here with you. It's my first talk in English, so I'm very grateful with you for your patience. Well, you all know that Kubernetes is a platform technology that significantly help us with sustainability, optimizing the use of our hardware resources and maybe physical resources. Different cloud providers also adopt these practices, and today provide different tools that allow us to measure the generation of CO2 and be able to take action in construction with good practices to mitigate this aspect. But they really try to understand is what's happened within Kubernetes when it comes to being sustainable. So we have two main challenges for our perspective. The first challenge is understand and measure. Understand the relationship between the services that we make available in Kubernetes and the energy consumption that they produce. To understand, we have to be able to visualize and observe what's happened between our workloads in containers and the consumption of our hardware that they make. That is why I'm going to mention some hardware and Linux kernel terms that I invite, if you don't know, touch me later and understand together. So here we see hardware, humans, servers working together to bring different services through Kubernetes and pods. And okay, how can I do to measure and understand the quantity of energy that consume? So I can show you an ally in this challenge, that is Kepler. Kepler is an open source project, acronym for Kubernetes Efficient Power Level Exporter. And as its name indicates, we are talking about energy efficiency and exporting data. Kepler we can deploy this like as operator by Helm, OpenShift Community Operator, Manifest, or RPM. How it's work? How does Kepler work? At a high level, Kepler intercepts system calls and collect hardware indicators with different techniques, K-proof, trace points, and different performance counter obtained from C groups, for example. And together, thanks to its component development in eBPF. In case you don't know what is eBPF, has its origin in the Linux kernel that can run a sandbox software or programs in a privileged context such as operating system kernel. And it used to safely and efficiently extend the capabilities of the kernel without requiring to change kernel source code or load kernel new modules. It's highly used today in service mesh, CNI to add observability, networking security, traceability, and profiling functionality, which allows you to work in user space, communicating with the kernel space, and correlate data from different hardware events like interim requests, CPU cycles, RAM memory speed, among others, and convert them into metrics to export to Prometheus, observability and metrics management tool, Prometheus. This is not only due to the capabilities of the Linux kernel, but they are supported by technologies such as ACPA, Advanced Configuration and Power Interface. Is an open standard that operating system can use to discover and configure computer hardware components, and RAPL, running average power limit. It's a power estimation feature in modern CPUs from Intel or AMD, and is very used by the green software community to obtain accurate energy measurement for the CPU and DRAM components. So Kepler obtained all of this data for this different component. This is the architecture of Kepler. And additionally, and very extremely useful, Kepler have some models of machine learning that train to predict and calculate what our energy consumption will be based obviously on the metrics previously collected in your workloads. Like, can you see, Kepler model servers have an online trainer that maybe work to estimate the energy consumption, and have an offline trainer to train and recollect response from prompt query. So in these two specific models, the objective or goal is calculate with different linear regression and others algorithms what or how much energy that consumed based on the previously consumption. And then what we can see with Kepler, we can see dashboard that show us different energy aggregation of the state of use of our resources, like pods or namespace. Here we can see total pod energy consumption in different pods, and total energy consumption by namespace in different cases, and others time series data to understand the behavior of energy consumption. And Kepler is not alone, and I take this for Red Hat presentation. Is currently campaigned by other projects such as PIX, Power Efficiency Aware Current Scheduler. Some spoiler alert for other tool that I will see next, and Project Cleaver, Container Level Energy Efficiency BPR Recommender, use machine learning models to predict and tune pod resource to optimize performance based on energy consumption of the CPU or GPU. So this is the first challenge, and this is the first tool that can we use to resolve. The next challenge is more specifically that is reduce and measure. So we already have a complete successful measurement with Kepler in our scenario. Maybe change humans for automation, but hardware servers all working together to bring services through Kubernetes and pods in different cloud provider too. And how can we reduce the energy generation and consumption of our workloads? Can we control? Can we schedule or take other actions? So here is where QGreen appears. QGreen is a current operator which create the necessary custom resource definition to be able to reduce or sleep mainly the number of pods we use during different time slot of our workload. Is working that we see with a custom resource definition in our deployment, and the architecture is the custom resource definition called sleep info specifically. Deploy a controller that QGreen can allow to modify the current state just in cron job and deployment scope. So we can define working hours metadata and specification of weekdays and what time to sleep our pods and what time zone. And we can also define exceptions or exclude different workloads to not apply the schedule sleep info. So QGreen also, it will give us the possibility of have a dashboard displaying the status of our CO2 generation and a general overview of others metric. How do we see the impact of using QGreen on our Prometheus metrics? Well, we can observe that if we generate the habit of recognizing what our optimization space are or where our pods sleep, we obtain a more predictable degree of utilization, and that gives us greater benefits, not only in terms of sustainability. In case of memory and CPU, we obtain a more constant consumption for what are resources that we can call non-productive, or maybe are the first workload that we can apply sleep info resources. But the reduction in computing resource leads to a reduction in the need for awake pods, and therefore to the possibility of decrease in node utilization. So if we have a node autoscaler technology like Carpenter or the autoscaler of Kubernetes, we also obtain cost optimization in the use of infrastructure and a double gain in emission reduction. So at last, QGreen gives us a great tool to calculate the CO2 reduction in relation to the number of pods we have running. This is based on an incredible measurement exercise that his team, and together with team of ecologists, I think, we able to obtain. So these two tools, Kepler and QGreen and others that appear in the industry, are great allies to begin our path towards a more sustainable Kubernetes environment. Just at the end, I only leave you agnostic recommendation for any tool or any process to be more sustainable in use of containers. Maybe grouping by resource consumption, minimize waste, and improve efficiency, but right size container and to use to limit the CPU and memory consumption, lightweight base image and multi-stage build, oriented to minimize the storage utilization, and maybe together with container image lifecycle, propose a really optimized use about storage. Resource and quotas and limit, set limits and of our hardware resources to our workload is important to minimize the waste and improve efficiency, like use container orchestration, of course, with Kubernetes, observability and debugging to understand what happened with our workloads in our container or Kubernetes environment, auto-scaling to use a minimal resources to cover the demand of the services, and CI/CD optimization, maybe talking about not run build or image building all the time, just trigger the build that really necessary to build our system or services also. So it's a lengthy talk. It's very quickly. I'm sorry if I run very quickly, but so that's all for today. I hope you enjoyed this session, and I appreciate if you can take a few minutes to answer a short survey that I put in the chat then, and I hope to see you soon. Thank you very much.
Thank you. Are there any questions? If not, I will pause the recording and we will do a short 10 minutes break before we take on the second half of the event. And after the break, we will start with Adrian's talk. All right. See you all back in like 15 minutes past, I would say.
And we can talk to each other, right?
Yes. All right. Next
Okay, well, hi, everybody. Thanks so much for inviting me to speak here. I used to be part of the CNCF when I was at AWS. I was actually on the board and was involved in getting AWS to join the CNCF about 5 years ago. I left AWS about a year and a half ago. I'm now independent, sort of semi-retired consultant advisor. But the last thing I did at AWS, I spent about 2 years working in the sustainability team and built out some experience and understanding there. And then most recently, I've been a member of the Green Software Foundation, which is a sister organization in that it's under Linux Foundation, operates by the same kind of rules as CNCF, but it's specifically focused on green software. So most of my current activity is with the GSF, and we've been having some joint discussions, particularly with the Kepler team. So I'm going to go through a talk, which is an updated version of a talk I gave last March at the KubeCon London conference, which talks about what is currently going on with cloud providers. So I will share screen. All right. Okay. Hopefully, can everyone see the screen okay?
Right now we can see the speaker notes.
Oh, really?
So the keynote overview.
Yeah. Where do I? Where is that option? Keynote. That's annoying. Play. No, you should be seeing. All right. Are you seeing the speaker notes now, or are you just seeing the screen itself?
Right now it's the keynote like overlay the app. So you see on the left side the slides, and then in the middle.
Haven't had that problem with Zoom before. Let's just see. What do I have to do here to make this work? Because I thought it would just be what I was seeing. Okay, so there's that. And then I want to switch. Let's just stop sharing and see if I can get Keynote to do what I want it to do. So I do that, and then I do. All right, is that better?
Yes.
All right.
Great.
Okay, I just did it. I had to hit play on the presentation before I shared the screen. Okay, sorry about that. All right, I think I've done enough of an intro. So what I'm going to talk about is a little bit about why sustainability matters, why is this hard, some terminology, mental models, what's going on in the cloud, similarities and differences, how to measure carbon in the cloud, and some things that I think developers need to build. Just an apology, a lot of dense content. I don't have a graphic design budget to make it look nicer nowadays, but I'm going to throw in some pictures. And this is a picture of Lahaina earlier this year before it all got burnt. And that kind of leads into why does sustainability matter? We want to leave the world habitable for future generations. We're currently breathing a lot of smoke. Places we live or like to visit are on fire or underwater or whatever. There's also a bunch of regulatory compliance. There's market transition risks. Think of yourself as, so let's say you own the Miami Beach spark plug company. You're not going to be selling spark plugs in another decade. Physical risks to business assets. Your Miami Beach location is going to get flooded. So you want to become the Denver electric motor commutator company or something like that. So those are the kinds of business transitions. Green market positioning, we're interested in products which can be marketed as green because buyers quite often want to buy green things. There's a lot of employee enthusiasm. We're seeing that as a very strong effect. It's usually underestimated that people want to work for companies that are ethical and particularly the sort of canonical thing is your kids come home from school and say, what's the future of the planet? What are you doing about it? And there's also quite often the green option is reducing costs now, but in particular, it reduces costs in the future. And then for some organizations, particularly the big fossil fuel companies, there's a social license to operate where they're trying to figure out how to be more sustainable and be seen to be more sustainable so that they have a future that they, just to operate at all. On the regulator side, there's a lot of things going on right now. Companies need to report emissions, assess climate risk, and pay border taxes on carbon. California just signed into law SB 253 and SB 261, which is reporting on carbon and also reporting on climate-related risk. EU carbon border tax just kicked in. The EU Corporate Sustainability Reporting Directive is active. Everyone has to put, if you do business in Europe, you have to work with that. And the SEC has a proposed rule, which is a bit more stalled, but it's along the same lines. California is moving ahead of the US SEC rules effectively. So things we can do now. If you're a developer, you can optimize your code, make it run faster, use better algorithms, turn off logging a bit, reduce retry storms and work amplification. All these things will help. Key thing about retry storms, if you look at a system, quite often the times when that system is at 100% utilization is caused by a retry storm. So if you size your system for the busiest part of the workload, quite often it's when the system is unhappy like that. So if you make the system bigger so that it survives a retry storm better, you're actually going in the wrong direction. There's a whole lot of detailed work that could be done there. Have a whole presentation on that somewhere. On the operations side, you want to run those workloads with high utilization, more automation, relax some overspecified requirements around availability and things like that, or data retention. So hopefully you can archive and delete data sooner, deduplicate it, compress it better, but also choosing times and locations carefully, as was mentioned earlier. Okay, so how do we measure carbon? And why is this hard? So because we just have two numbers, how much energy is it, and what's the carbon content for that energy? But we have to understand the scopes of carbon. And the scope 1 is the fuel you consumed. So if you have a car, it's the fuel you bought, that you burn, it's the gas you burn, it's the fuel you burn. Scope 2 is the energy you use, and the grid mix comes from whether that energy is renewable or not. And then you want to store that energy if you can in batteries, and you want to switch all of your uses where possible to electricity and renewable electricity. And scope 3 is everything else. It's basically your supply chain and your investments and the things where you get things from, and the energy used by the consumers when they consume your product. So if we look at a data center, there's a mix of energy coming in. There's a backup generator. There's more and more use of renewable diesel fuel in backup generators and fuel cells and things like that. The construction of the building is scope 3, and delivering the racks and of machines, that's scope 3. Okay, so scope 1, 2, and 3 laid out there. If you look inside a data center, the energy comes in, it has to be distributed. Some of that energy is lost in distribution. Some of that energy is lost in cooling. So the efficiency of the data center matters. But again, that applies to scope 2. And then scope 3, as I mentioned, is the building and the racks. So suppliers need to report scope 1 and 3 to you, and you need to report scope 1, 2, and 3 to your suppliers. And this is all laid out in the Greenhouse Gas Protocol. A very useful paper by Microsoft explains these different scopes, but also that the scopes matter who you are. So if you're a cloud consumer, everything is scope 3 upstream. But if you're a server manufacturer, manufacturing that is scope 1 and 2. Any cloud operations you have is scope 3, right? And if you're a cloud provider, you're trying to manage your scope 3 for manufacturing your cloud. The operations is 1 and 2, and then disposing of things is scope 3. So this scope 3 is a little confusing, and it's effectively double counted. Everyone counts it multiple times, but it's very important to make sure that people can't just push their carbon footprint out to a supplier and say, I'm not responsible for it anymore. It makes you responsible for your suppliers. So another thing that's happening is the carbon content of energy is tending to zero as we're getting very good at putting in lots of solar and wind and battery power. And so Scope 3 is starting to dominate carbon footprints. And for cloud regions in the EU and the US, that actually happened a little while ago. So it's the energy times the carbon content plus that supply chain. So the supply chain is becoming more important. If we just look at Europe here, and this is based on some data from a year or two ago, you can see here that Scope 3 is kind of fixed. It doesn't really matter which country you're in. Scope 2 is very high in Poland and very low in Sweden. And in Sweden and Norway and France, Scope 2, 1 and 2 is less than Scope 3. But this doesn't take into account the energy generated by the cloud providers, which offsets most of the Scope 2 here to close to zero. So in Europe, it's primarily Scope 3 that matters. If we look around the world, electricity maps have a nice map here. You can see the green bits are places where the carbon intensity of the grid, not including what the private power generation, where that's green, and the brown and the red, it gets worse and worse. So some differences across the cloud providers. AWS doesn't provide any Scope 3 information. They say they're working on it. I complained about this. Somebody wrote a story about it. I've heard that they've actually publicly said they are working on it and they will release it, but there's nothing out yet. Azure came out with a really detailed Scope 3 paper. It's very useful. And that was in 2021, so a couple of years ago. And Google also has a detailed Scope 3, calculated very slightly differently, but not materially different. So you can get quite a lot of good information on those. And the way that Scope 3 is calculated, you have your emissions of cradle to gate, like what did it take to make the machine? And then you basically have to count up the hardware, figure out how much hardware each customer is using, and commit the customer emissions to the hardware and the services they use and go right through the system. So they describe that method. So how can you reduce Scope 3? The main thing is use less hardware, and you do that by increasing utilization as well as optimizing your workloads. So one thing you can do is use hardware for longer before replacing it, and we've seen cloud providers increase the amount of time that they depreciate their hardware over sort of 3, 4, 5 years, something like that. So that means that the energy for building it is amortized over more time. If you use the latest hardware for anything new you deploy, that's going to be faster and more efficient. The hardware footprint of a machine in a rack isn't actually going up that much, but the power of the machines is going up much faster. You can switch to ARM-based architectures, and AMD architectures tend to be more power efficient than Intel architectures at the moment. Intel has some work to do, and that will eventually change. So using fewer, bigger systems is actually going to help you because the overhead of the box is significant. The packaging, the metal, the power supplies, all those things. So if you use fewer, more powerful boxes, that actually helps if you're allocating nodes. And then the transportation contribution is very small. So Scope 3 really doesn't change around the world. It's a fraction of a percent. And if you go, the Bovista have a nice database of estimates here, and you can go and find one of the links here is to a standard sort of Dell machine, and you can go look across the Dell platform, Dell product range, and see the difference across different systems. Okay, Scope 3 is about hardware, so I'm going to decline it to be an ops problem and just think of, okay, from a developer point of view, what are we really worrying about? We're worrying about energy and carbon content. So what we want to know is how much energy does a kind of line of code use? And there are a few things for JVM energy monitoring and maybe Kepler for the pod level. If you're trying to figure out how much energy a transaction uses, the software carbon interface, software carbon intensity spec is something that the GSF has been working on to define. But you want to really know how much energy a workload uses, which means you need to know how much a container uses, and then you need to know how much a specific cloud instance uses. And cloud providers don't tell you those things. You've got to go and infer them. So if you're in the data center, you can measure this yourself. There's RAPL as one interface. Redfish is an interface that you can use to get at this kind of data, or you can measure it yourself using a little power box, or if you're using a Mac, you can turn on Activity Monitor, but then you see that Activity Monitor is using more power than anything else on the machine. So you have to be a bit careful about how are you measuring this stuff and what the influences are. So it's a bit of a pain to measure, but you can get that. Now let's look at the carbon content. So what is the grid mix in that location? When was that measured? Sometimes the data you can get for free is for last year. It gives you the average for the year rather than a prediction of what's going to happen in the next day, which is what you really want. Do you have hourly grid mix? Google does do this, but doesn't share it really. Do these grid mix numbers stay still? So you've got a particular hour, you've got a grid mix number for it, you've reported that. Unfortunately, the grid mix for that hour can actually change over time. I'll explain a bit sort of later how that happens, but it's an estimate and the estimate gets better, so it changes for that reason. But also offsets can be bought later to offset it down to 0 or to some lower level. So the numbers don't stay still. And then the other thing is you want to know how much private cloud provider energy was used. There's some data from Google provides, but mostly they don't provide information about this. And then how much of this data was bought on the market, which is renewable energy credits. How much bundled and unbundled? I'll explain a little bit about the difference in a second. So how can we reduce the carbon emissions of the systems we build? So saving carbon is directionally the same as saving dollars, and one good proxy for this is if you can save money, you're reducing carbon. The problem is that the carbon per dollar varies a lot. You could save $1 here and it would make very little difference to the carbon, and $1 somewhere else, it would make a lot of difference. So let's focus on how to measure carbon. We're used to reporting and optimizing all these different metrics. So really, I think carbon should just be another metric that you report. And you really want to measure the carbon emitted by a workload. So this is zooming into my little diagram. You get grid mix from the local utility bill. Usually that's a month or so in arrears. You can get some real-time estimates of grid mix from places like WattTime and electricity maps. And really what you want is a prediction of the next 24 hours, updated every 12 hours. That's one of the data sets that you can get. Power usage efficiency accounts for the losses coming through from the energy supplied to how efficiently it's used, and it varies a lot around the world and from data center to data center. And it also depends on how you're measuring your data center. Different data center architectures will be different, affect the way it's done. So that's another thing you need to know. Now you know how much power gets all the way to the machine. So this carbon basically is going to be the power mix multiplied by the PUE ratio, multiplied by the capacity that you're using in your environment, and then you need to know how much emissions there are for each of that, for that capacity. Unfortunately, there's two different ways of calculating this, the location and the market method. Location-based just uses the grid mix coming into the building at the time. Google uses this, and it's usually hourly, 24/7. So hour by hour, you're looking at the utility grid mix coming with data from somebody like Electricity Maps or WattTime. The market-based method, that method by its definition cannot take into account the fact that somewhere else on the grid, you own a power station, you're generating all this green energy. That data is not included in the location-based by definition. The market-based method does include, it's basically what you paid for. So if you're generating energy, that means you don't have to buy the energy that's coming into your data center because you're generating excess elsewhere. It's a little bit like in your house when you've got solar power and you're running the grid backwards. That's a market-based method. It also lets you buy renewable energy credits to create a custom grid mix for the data center, which is usually averaged over a month, but is usually trued up at the end of the year to make whatever number you wanted to get to by buying extra renewable energy credits. So the problem here is AWS and Azure use regional market-based. So they basically say we only count the generation that's connected to the same grid. right? So those electrons can flow from our solar, farm to the data center that's in that region. Google have had a claim since 2017 that they've been 100% renewable. That's global market based, so they were using generation in USA and Europe and counting that against their energy use in places like Singapore. A little bit of a side eye on that. It's okay in the old days, but now people don't really think that cross-country global renewable claims are a good one. So Google have now moved to location-based for their current 24/7 work, and they don't provide market-based. So what we've got is completely different models being used across the different cloud providers. But as we decarbonize, it's going to matter a little bit less. So problems here. The utility bills are going to be late. If you're in some part of the third world, it may be very slow to get data. So if you want to do data for the whole world and you're in all kinds of complicated places, it takes a long time. So it takes Amazon 3 months to actually generate the data, to share the data, partly because some of the data sources are very slow. Power purchase agreements are contracts and build power consumption. Amazon has over 20 gigawatts of PPAs. Microsoft and Google have over 10 gigawatts. Amazon has more because it's also offsetting all of Amazon, not just AWS. The delivery environment, all the warehouses, that's all included. Renewable energy credits are purchases of renewable capacity. Basically, somebody's generating power, you can claim the power the power from that on an open market. And these can be used to top up on top of PPAs. So generally, most of the cloud providers do most of their work with PPAs, and then they adjust and top up by buying and selling RECs. So they have excess energy, they sell RECs, and where they need more energy, they buy RECs. Now there are good and bad RECs. They're also called guarantees of origin in the EU. And local market, this is good, but if you're going cross-border, the energy can't flow to you, and there's a whole bunch of things that effectively end up as greenwashing and cause other bad effects. There's links to this. I'll share these slides after the talk, but I need to move on so we don't run out of time. All right, so grid mix. It's changing every month, mostly getting better over time. We're starting to get 24/7. Google and Azure publicly working towards 24/7, then the Cloud Carbon Footprint Tool estimates don't include PPAs or RECs, so they just basically are giving the location-based data. And there is a startup working on some energy trading here. If we look at how this works, one of the things is that the RECs and PPAs aren't included in the grid mix. This is private data. And any generation that happens doesn't flow into the grid. It's consumed directly by the people that have got the power purchase agreement in place. So the cloud providers are using some fossil energy, some renewable energy. That's the power mix you can see for location-based. And then there's this renewable energy and some credits, and that's kind of the mix. And then the other problem is RECs can be traded for up to a year. So the data for, once the year ends, you look at your mixes and you say, yeah, I'd like this one to be a bit better. So you go back and buy some RECs for it. Now, one of the problems in mature markets is that there's now so much power purchase and renewable and fossil is low, so that the cloud providers are actually generating excess energy and putting credits back on the market. And it causes the whole environment, because now we're using things like Cloud Carbon Footprint, are looking at data that is really a long way different from what's really happening. All right, PUE, as I mentioned before, is the efficiency of a data center. AWS doesn't publish PUE. There's some estimates that the PUE isn't bad, it just doesn't publish it. Azure and Google publish PUE in some detail. If you look at the capacity, you're trying to figure out how much capacity you're using. Compute and storage is relatively easy, but then you have shared instances, network equipment, all these things. And if you're building a multi-tenant service and want to report carbon, you've got to figure out how much capacity to allocate to each of your customers and how much is overhead you should own yourself. And this is a big problem that everyone is struggling with, and we need better algorithms for this. Kepler is a huge help for getting the workload itself figured out, but you still need to attribute and allocate to your customers. Then you need to understand how much power each instance type, storage class, or service uses, where that's located, and how much carbon is emitted per kilowatt hour. Utilization changes, so if you have a low utilized machine, it uses a bit less power than a fully utilized machine, but it's not fully proportional. Obviously, it doesn't go to zero. If you're not using a machine, it's still dissipating power. Somebody else may be using it, or it may be sitting idle, but the machine is still sitting there consuming carbon, emitting carbon. Bovista has some estimates here of some of this data, which is about the best we have so far. All right, some takeaways. What can you do today? The main thing is use less stuff. Just be more efficient. AWS, this is 2021. They had 13 regions that were better than 95% renewable. And this is showing where all of their wind farms and solar farms are, and they have some in India and Indonesia, China, Australia. So there's quite a bit of renewable energy PPAs set up, basically dedicated resources for AWS, as well as in Europe and the US. In 2022, these numbers came out in the middle of this year. They've taken US and Europe from 95% to 100%. They've also added India and China at 100%, which still leaves Japan, Korea, Indonesia, Australia, Brazil, South Africa as, it doesn't say, but less than 100%. Azure doesn't have any renewable global projects in Asia, apart from I think one in Indonesia or wherever that is, Singapore maybe. And so you can rotate this little globe around if you want to see where they are, but most of their renewable energy is in Europe and USA. And Google in 2021, this is the carbon-free energy at data centers based in this. Again, this is location method 24/7, so they show much more carbon being emitted. But if you look at Taiwan and Singapore, it's almost all non-renewable. There's very little green there. And they're 66% globally on an hourly basis. So that was 2021. If we look at 2022, that actually slipped slightly from 66 to 64%. And they've added a few regions. Some got better, some got worse, but Google didn't really make much progress year on year. But they do have a commitment to get all of these green by 2030. So the net for this is use any cloud provider. US and Europe are pretty clean. Asia is where the problems are. AWS has the most green energy across Asia, particularly China and India. Everyone's buying gigawatts of renewables, but this is all better than a typical data center. So that's kind of the net on sort of how to pick regions. And let's have a quick look at the APIs and schemas and sort of what the data looks like. Yeah, AWS has a custom carbon footprint tool which has a CSV download as its only API. It's very crude. It doesn't give you a very good summary. It's really only useful for sort of the annual report level kind of things. It doesn't, and it's delayed by 3 months and doesn't have scope 3 in it. So this is inadequate. It's been out for 1.5 years now, and they haven't really updated it. So we're just waiting for them to come out with something better. There is a team working on something better, but we haven't seen anything yet. Azure has an OData API, which is pretty nice. You can get all of this interesting information. It's much more accurate. You've got a data by service and by account and by region rather than just country. Or in fact, AWS, it's just by Europe and US are region. They just bundle all their regions together. So this gives you the actual down to the region, and it gives you scope 3. Google, they export their data into BigQuery, and you have a schema there. You get it down to the zone level, so they've got more resolution there. and more resolution on on how much carbon it is, down to 1/10 of a kilogram. And they've got placeholders for market-based, but they don't provide any data there. And they do have scope 3. So 3 very different schemas. And they're all monthly updates. None of these will give you real-time data. So what I wanted to see was real-time carbon. So I proposed a standard. I proposed this back in March. I would like to see the same data from all cloud providers and on-prem data centers as well. I think they should all have the same resolution as existing monitoring tools. They should update every minute. I think it needs to go down to zone. It should be you should be able to get data down to containers and things like that. We should be able to support that. And I want accurate data, and I want location and market and scope 1 and scope 3. And the problem with this is that the energy data you can estimate, but the CO2 data is going to change. So we'd have to report some of these things as ranges, as confidence intervals, and those confidence intervals would be tight in some places of the world and wider in other places, and they would tighten up over time as you got better data. Anyway, so that was what I proposed. And the Green Software Foundation, there's a PRFAQ I wrote that says this is what I'd like to see. It was a press release for if this thing got announced. So how does this relate to Kepler in particular? So Kepler, when it's running in the cloud, is using models that were trained outside the cloud and other estimates of what's going on. It doesn't really know the carbon intensity. It doesn't really know the instance energy. So what I want to do is feed actual data from the cloud provider into Kepler, so Kepler can do the cluster and give me my Prometheus metrics and do all this kind of stuff. I think instance energy changing updated every minute from the cloud provider would be good enough. Carbon intensity is sort of an hourly, or it changes by hour. I think that's fine. So those are the feeds that I'd like to see. And Kepler would process that into something for a workload. So we've started this project, the Real-Time Carbon Footprint Project, and the basic thing here is all models are wrong, some models are useful. We want to make the cloud carbon footprint models less wrong and more useful. It's never going to be perfect. If you go visit the Miro, you can see the end-to-end flow of Kepler's on here. You can see all the different things, like where did we get the data? What are the APIs? We're gradually building this out so that we get a full documentation of where does every piece of instrumentation and reporting and data sit? What is the actual schema that they produce? Who consumes that schema? Can we get an end-to-end flow? And then we can work out where we need to insert new data from the cloud providers and where the gaps are. So this is kind of the comparison of what I'd like to see. Just all side by side. And if we had that, what would we do with it? We'd be able to reuse our cost and performance optimization tooling for CO2 optimization. We just have metrics coming in minute by minute, along with all the other metrics that all our tooling normally sees. We could build things like a carbon peak flattening scheduler, move work to other times and places, kind of as we were hearing about in the earlier presentation. Those kinds of schedulers have to feed it the right information so that it really knows how to reduce the peak load for carbon, because you want to reduce the peak. Capacity planning is based on peaks. The average actually doesn't matter. What matters is the peak. So if you can get the peaks down, then actually everything else works. The carbon for that location will go down. We need to do SaaS provider attribution allocation tools for per customer reports. And then we also want to have some planning tools. So as an example, you could run your own Kafka on EC2, or you could run AWS MSK, which is managed Kafka, or you could use Confluence product, or you could use a Red Panda product, which is sort of equivalent, or you could use Kinesis, which does roughly the same thing. What's the carbon footprint of each of those? Is there any way to estimate that? And if anyone knows, I'm actually interested in another side project. I'm trying to come up with estimates of things like this. Anyway. One more thing a few more things that are interesting. If you're trying to exchange carbon information, across boundaries between companies. There's an API for the supply chain carbon data developed by the World Business Council for Sustainable Development. So this is a really interesting piece of work. The idea being you can instrument your supply chain and actually pass the carbon up and down. And then we talked a lot about measuring carbon. We also need to think about the impact that the climate change is happening on your business. So this is the reverse direction. This is physical risk, where your buildings are going to be underwater or on fire or taken out by tornadoes or hurricanes, and market risk because you're operating in a business, say you own gas stations or you manufacture spark plugs, and that industry, because of what's happening in the market, is moving to electric vehicles that don't need gas stations and don't need spark plugs. So that's a market transition, and there are different models, and osclimate.org, which I was previously involved with at Amazon, has some open source models around this, which are quite useful. All right, just a few things then that I think developers need to build. We should add energy instrumentation to applications. We should have these attribution allocation algorithms. Kepler's a good example, but we need more kinds of algorithms like that. We need data lakes to collect these measurements. We need to instrument IoT and mobile instrumentation right the way to the edge. Think of a delivery truck, and you just measure how much diesel fuel your delivery trucks use that day. That's kind of the level of detail that a lot of carbon footprint of deliveries is right now. But then you think about the Amazon Rivian instrumented vehicles they're using for deliveries. They can tell exactly how much energy was used to deliver that package to you and this next package to the next person down the street. That's super high detailed instrumentation. Energy usage dashboards. We have to build these protocols for interchanging, like Pathfinder. We need to have better models for moving energy to carbon. We need impact and risk models, and then we need these sort of schedulers for peak flattening. So that's what I had. And if you want to we have some issues and things in the real-time cloud that are open. It's all on GitHub in the same way that CNCF runs. So again, you're welcome to get some inputs and more questions there. So that's what I had. Hopefully not too much over time, and we can see if there's any questions here.
Thank you very much. Are there any questions?
It's a question here about location-based being more honest. The problem is that location-based creates no incentive to build power stations because it doesn't apply. So the fact that Amazon and everybody, they have tens of gigawatts of power stations that they've invested in, that's the energy they buy. That energy is not included in location-based by definition. Location-based is pure location-based assumes that you do not generate power, you only consume power. Organizations that do both have to include somewhere the fact that they are generating power in this market. And that's that you cannot claim the negative location-based thing that you have a power station somewhere generating green energy in your reports. So that's kind of the issue. That's why market-based has the right incentives to have people invest in and it has caused people to invest in power. But the other thing is that green energy is currently the cheapest energy you can buy. So this is all driven mostly from financial considerations. If you need 100 megawatts of energy somewhere, the cheapest way you can do that is contract for somebody to build a wind farm. And that's cheaper than buying it from the grid, and it's cheaper from everywhere else, which is why the market-based method works on this. Fundamentally, everybody should be reporting both, and there's some ideas around for revising the methodologies to actually resolve this. So basically, both these methods were invented at a time that didn't take into account that there would be very big generator and consumers out there. And there is no way to compare apples to apples across these providers. And it's not greenwashing. Both of these methods are covered under the Greenhouse Gas Protocol. Everybody's doing this. the right way. And I think everyone is really doing the right thing. I think the cloud industry in general is doing extremely well compared to other industries. Most of the other industries are far behind in terms of their conversion to a green future. And they're all roughly at the same level. The biggest problem I have is that AWS is much less transparent than Google and Microsoft. They just aren't releasing as much information, even though in many places they probably have better data or better results, particularly in Asia. So just looking at these questions here. Yeah, and the biggest challenge in the short term is to get everyone to agree to do this. And I have people from Microsoft and Google on the standards group within GSF. AWS isn't a member, but I know people that work there. So I'm trying to get this standard defined very clearly, get everyone to agree that it's useful, it's needed, and then we'll get all of the end users that want this energy to go beat up on the cloud providers and get them to say, you need to do this. So that's basically what we're trying to get done. Okay, those are the questions I saw in the chat here. Any questions on? I don't actually know about AWS and SBTI. A lot of the time, Amazon, it's not AWS, Amazon as a whole is an extremely complicated organization, and they are optimizing for the big picture of reducing carbon for Amazon as a whole. Quite often, some of the models like SBTI and things like that actually just are trying to persuade that the models are too simplified. And internally at Amazon, sometimes they've said, yeah, this would cause us to actually do the wrong thing by trying to comply to it. But anyway, we should move on. Thank you.
All right, thank you very much. So for the next half an hour until we wrap up this event, we kind of circle back a little bit to the beginning, where I introduced the tag, the event, and everything. So now after these talks, we will again circle back to the working groups we've been working on, giving some short introductions what the tag has done, and we start with comms, and then we go to green reviews and a very short look into the landscape as well. Kara.
Thanks, Leo. So my name is Kara Delia. I am the comms co-chair. We are, let's see, okay. Right now we have a charter proposed, and essentially this is the marketing arm of the tag, which is extremely important for getting information out about what's happening in the tag, but also as another way for folks that want to create or to contribute something on a non-technical basis or non-code basis that they can leverage. So we are member neutral contributions, and the whole goal is around ecosystem development, working with other organizations, some that have been previously mentioned, like Green Software Foundation, OS Climate. The goal is to be collaborative in our approach. Our goals for the working group are creating a marketing strategy, and that's going to be around digital media, public relations, web content, and blogs. And we are, again, working to collaborate with other projects, and importantly, communicating this not only to our own community, but outside of our community, so we can get more involvement, hopefully from some of you. We do need sub-project chairs. Our 4 areas of focus for sub-project chairs are events, blogs, social, and tech. And we have a list here. I'll make sure these slides go out afterwards. These roles are flexible to change, and any type of contribution is helpful. We are looking for chairs, so if you have a passion around blogs or social or events such as this, happy to have you contribute. Here is our QR code for our meetings. We actually just met this morning, and we do meet weekly currently because we are forming and norming, and there's a lot to do. We have a lot of backlog, and again, your help would be extremely valuable. And with that, I want to say thank you and hope to see you at a meeting or on Slack.
Thank you so much, Kara. Are there any questions for working group comms? If not, we can move to the next one, to next working group green reviews.
Hi, everyone.
Currently, we see the browser tab.
How about now?
Looks good.
Okay, great. So, hi, everyone. We are, Christina and I are the co-chairs of the new Green Reviews working group that we started in August. And so, a bit about me, I'm a software engineer at Grafana Labs. I live in a national park and I like birds. Christina, how would you like to present yourself?
Yes, hi everyone. So my name is Kristina Deochko. I'm principal cloud engineer at Mesto42 and I'm based in Oslo, Norway. And we decided to go ahead with a fun fact today. So I volunteer in an animal shelter and love amusement parks. That's my fun fact of today.
So the charter is available. That would be a great first start if you'd like to find out more about what the goals and non-goals and the scope are of the working group. We are kind of the first technical project of the TAG, and so we want to be able to help CNCF projects and their maintainers and users to review the sustainability footprint. So looking at energy, standard metrics, as well as potentially carbon. We want to create a pipeline for gathering these metrics and provide resources for folks, other engineers who wish to set up similar pipelines potentially. But primarily our goal is to provide reviews and assess the sustainability of those projects and provide suggestions to improve those. So we have a design doc that you can read through. What are we building at the moment? We're starting with a pipeline. We have Equinix infrastructure that is donated to the CNCF organization. We're focusing on the GitOps approach. So we're looking at Cluster API or Ansible. We want to create a pipeline with GitHub Actions that will be triggered by the release process, ideally, of CNCF projects. But we're also just trying to look at the integration test or whatever testing there are available in the CNCF projects to determine the functional units, or create those tests ourselves, potentially with K6, and create those benchmark load tests to assess, to determine the functional unit and measure it. Christina, would you like to continue?
Yes, and when it comes to the CNCF projects that we are collaborating with, our goal is to first start small, and therefore Falco team was willing to help us out and collaborate with us on this. So this Falco will be our first pilot project that we will be targeting our implementation towards. But with time, once we mature and once we test the tooling that we are building, we hope that we can extend this to more CNCF projects. So if any one of you present here today or watching the recording afterwards are the maintainer or are contributing to an existing CNCF project, do check out a GitHub issue we have on our project board, where we are gathering interest from the CNCF projects who would like to be at the early phase of testing out our tooling once we mature. And when it comes to the data we are gathering and the way we're going to be calculating the sustainability footprint of the CNCF projects, we are currently looking into utilizing data like the standard metrics that many site reliability engineers or infrastructure engineers are used with, like CPU or a memory usage. We will also be utilizing Kepler, and we will be utilizing the metrics that it gathers specifically that are related to energy consumption. And when it comes to the way we will be calculating it, the sustainability footprint, we are currently looking into utilizing Green Software Foundation's software carbon intensity specification, but we also have an ongoing discussion as well on GitHub and in our working group meetings, where we are open for suggestions and ideas for any other specifications that we could benefit from when outlining the way we will be calculating this sustainability footprint score. And when it comes to contributions, we really need volunteers, and this is also the possibility for you to contribute from the technical side of things. So if you are technical yourself and you would like to contribute with your technical competence to the project that hopefully will make a significant and important impact in the CNCF landscape. So this working group is worth considering. So we have now a subsequent channel on the CNCF Slack called WG Green Reviews. So please join us. It's open for everyone. And we have our regular meetings on the 2nd and 4th Wednesday, 5 p.m. Central European time at least. And we also have our GitHub project board, where you can see all the ongoing tasks and completed tasks and the tasks we have in the backlog that we're working on. And our main and central document currently is the design document, where we are outlining the design of this implementation. So we are also open for input and suggestions there. Yes, I think this is it from us. So thanks, and I hope that we get to see some of you or all of you in our next meetings.
Thank you so much. Are there any questions for the working group Green Reviews? If not, the last one is from Marlo, a project kind of introduction to the landscape document, which we started like how much, like a year ago or something?
Yeah, I think it was a little over that. Should I get started?
Yes.
Okay. So I am Marla Weston. I don't have a fun fact today. I am a CNCF Environmental Sustainability TAG Chair. I'm also a cloud software architect over at Intel. So let's talk a little bit about the landscape, the purpose of the landscape, right? Why were we doing this to begin with? And it's basically, we wanted to put together like a whole set of resources so that people could easily find what they were looking for as far as enabling sustainability in cloud. So included into this was like how to do measurements if you're creating tooling, right? Specifics of use cases. So we had public cloud, private cloud, telco, finance, and AI/ML are currently sections in there. If you want to expand, please come join us. We also have different layers of solutions and what they look like, current research and toolings, and various sustainability initiatives. So we are one initiative. There's also GSF, and there's a variety of other ones available to get involved with depending on what your space is. So I'll go through a few things in the landscape doc. So we have this sustainable computing landscape, where if you look, we have basic structure. This is pulled in. Leo did a really lovely job of adding these, but it basically pulls in all the different sections that are in the landscape doc. So it includes data centers, methodologies of data centers, observability tooling, and infrastructure tooling. And here's the observability piece. So there's gProfiler, Power API, Kepler, which I'm super excited is now a CNCF project, Scafandra, the green metrics tool, cloud carbon footprint, all these different tools that are being used within observability. And of course, this isn't complete. This is why we're including this. We want people to add to it. And then infrastructure, which is in the sustainable cloud computing landscape. So there's the scheduling area, which is where you land on the nodes. That was the first talk today, so that's kind of cool that that's getting going, but we need to add the project to this document. Scaling, which is how you scale in a responsible manner. And then resource tuning. Once you get onto the node, how do you maximize your, not necessarily your performance, but how do you maximize your efficiency on those nodes? And there's two different things here. One is the landscape webpage if you just want to read it. So please feel free to scan this QR code. But additionally, we have the landscape source code, and we highly would like people to come join us and contribute to this. We just had a blog post, for instance, on Linkerd, and so they have promised to come back and add some service mesh piece to it having to do with Linkerd. I would really encourage, if you have a project you are working on or are familiar with that you don't see in the landscape, please add it. If you want to modify it in some way, because there's use cases we haven't listed that are specialty use cases, please modify it. We are super friendly about this. There's also a section for contributors. So in these documents, you can see all the people that have contributed, which is quite a few. Do you have any questions? I know that was really fast, but also we're at the end, and I think we're pretty close to overtime. And this is how to reach me. Here we go. If there's no questions, Leo, back to you.
Thank you, Marlo. And yes, this was the last presentation. I hope you liked this virtual event. As I said in the beginning, this is the first time we tried out a larger event organized by us from the TAG. So I hope you enjoyed it. And we will upload the recording afterwards. Thanks to all the speakers taking the time. It was very interesting, and I hope we can organize this maybe next year again. I think this was a big success. Take definitely a look at the website and check out some of the resources. Marlo, for example, mentioned the blog post about Linkerd. But as I said in the beginning, there are a bunch more, also about Kepler, for example, which we heard today a lot about. Tomorrow is also a very interesting one about the challenges of measuring energy, which goes very much in detail. So take a look at the resources, take a look at the recordings, the live streams. Hopefully there's something new you can learn, and hope to see you in one of the meetings. And thanks you all for joining. And I will stop the recording.